What an awesome video, right? I love that video. So at this point, you might be a little confused, and that's okay. Uh, Quantum chemistry and quantum mechanics is a even for professionals, it's a very kind of ill understood and confusing field. And in fact, Einstein didn't even believe in quantum theory. Like he couldn't put that in with what he knew about the universe. So that I think really says a lot about this field. But there are a couple takeaways. Electrons can be treated like particles and, oddly, waves. Now, this discovery is credited to Louis de Broglie. Okay. Now, the observation issue is used by Heisenberg to state that it is impossible to know the position and velocity of an electron at the same time. Because if you try to observe an electron, you have to bounce light off it, right? That's how we observe things. And we already know that electrons can absorb energy in the form of light. So how are you going to observe an electron without changing it? Okay, that's Heisenberg uncertainty principle. Now, the next guy to come along and really make a big difference here was a physicist named Schrodinger. And what he does is he describes electrons as waves, okay? And this leads to quantum theory. And what he does is he uses math to describe probabilities treating electrons as waves. And he comes up with a series of equations that are beyond this level. They're multivariable calculus, and it's crazy stuff, okay? Solutions to Schrodinger's equations are known as wave functions, okay? And what these wave functions do is they give a probability of finding an electron at a given place around the nucleus. So the cool thing about this is electrons do not orbit, okay? They're not like little planets orbiting a sun. They just don't do that. Instead, what they do is they exist in regions of 3D space. Okay, they exist in regions of 3D space. We call these regions orbitals, and each orbital and the electrons in the orbital are described by a set of 4 quantum numbers that are sort of the simplification of the results of the wave functions. Okay, now these quantum numbers are kind of like the address of an electron. So it's important to keep in mind that each electron cannot have the same address. All right, and so the first way that we can describe an orbital is using something called the principal quantum number. And this describes the main energy level occupied by an electron. All right, it has the symbol N. It's also called a shell. The values are positive integers, so 1, 2, 3, etc. Okay, as N increases, I'll use this diagram here. As N increases, so does the distance from the nucleus. Okay. And as N increases, so does the energy. And you want to keep in mind that things always want to have the lowest energy possible. So N equals 1 is the lowest energy possible. It's closest to the nucleus, okay? And so those atoms are generally very stable. The maximum number of electrons in an energy level is 2n squared. We're going to go over that again later. Once an energy level is filled, electrons will fill the next highest energy level. So we'll fill N equals 1 energy level, then we'll go up to N equals 2, then we'll go up to N equals 3, 4, 5, 6. And another important thing to keep in mind here is as the energy levels get higher, the differences between the energy levels get smaller. So that has some pretty weird effects when we're trying to describe the electrons, but we'll get to that again later. All right, the next way that we can talk about orbitals, we're still describing orbitals, is the angular momentum quantum number. And this describes the shape of orbitals. So the shell describes the distance from the nucleus of the orbital. The angular momentum quantum number describes the shape of the orbital. Okay? It has the symbol L, okay? And it's also called the sublevel or subshell. I'll use subshell mostly because I use shell for the energy level or for the principal quantum number, and subshell for this. And the number of shapes per energy level is n. So for example, the first energy level has one subshell. The second energy level has two subshells. Okay? The possible values of this L are 0 up to n minus 1. So if I start to build myself a little table here, ignore this one for a minute. So here are my energy levels. Here are my shells. And here are my subshells. So in the n equals 1 energy level, okay, the only possible value for L is 0, right? Because it's 0 up to n minus 1. So if n is 1, then L is 0. If n is 2, then I could have 0 or 1. 3, 0, 1, or 2, 4, 0, 1, 2, or 3. Okay? Now, these 0, 1, 2, 3, these are generally described with a letter code instead of with a numerical code, because as you'll see, there's lots of ones and zeros, and everybody would get really confused. So the subletters, just increasing angular momentum quantum number, are S, P, D, and F. Okay? And you'll just have to remember SPDF, super PDF, I don't know. Something, find yourself a way to remember SPDF. All right? So what do I mean by shapes? Well, an s orbital is spherical. Okay? You have to kind of keep in mind that we're talking about 3D space here, right? So there's an x, a y, and a z axis. A p orbital has a dumbbell shape. Okay? That's what we call this shape. This is dumbbell shape. D orbitals start to get very complex. And the f orbitals are just really crazy. Most of them have like this dumbbell shape lobed, but there are some other crazy things in there, okay? And I'll show you those a little bit later. I do want you to know that an s orbital is spherical and a p orbital is dumbbell shaped. Those are important things to remember. All right, so the next quantum number is the magnetic quantum number. And this has a symbol m sub l, or in your textbook it's just m. Okay? This is the orientation of the orbital in 3D space around the nucleus. Well, what the heck do I mean by that? Well, a p subshell, which remembers that dumbbell shape, contains 3 orbitals that are aligned along different axes, right? If you were looking, this was the example that I gave you for this shape, okay? So this is a dumbbell shape, and it could be lined up along a y-axis, an x-axis, and a z-axis, okay? So that orientation leads to 3 orbitals that all have the same shape, okay? The possible values for the magnetic quantum number are all integers from negative L through 0 to positive L. All right, so I think having the table will help us with this again, okay? So anytime that you have an s orbital, L is 0, right? That's spherical. How many orientations can you have for a sphere? Well, 1, okay? It's spherical. So m sub L is going to be 0. For L equals 1, so a p subshell, you could have magnetic quantum numbers of -1, 0, and 1. For a d subshell, you could have -2, -1, 0, 1, and 2. Okay? And since each of these orientations is its own orbital, that means that for an s subshell, there is one orbital. Okay? So s has one orbital. P has 3 orbitals. D has 5 orbitals. So what would F have? That's right. F would have 7 orbitals. Okay? -3 through 0 to +3. All right? So each of these are orbitals. Now, so those first 3 quantum numbers describe the orbitals in which we find electrons. Okay? But I told you already, each electron can't have can't have the same address, right? It can't have the same set of quantum numbers. And each orbital can hold 2 electrons. Okay? Each orbital can hold 2 electrons. Maybe that's important enough to write down here. Well, how do we differentiate the 2 electrons in this orbital? Okay, I'm going to skip past that for a minute. And that brings us to spin quantum number. So as it turns out, electrons spin on an axis much like the Earth does. So you can think of this as sort of spinning clockwise about that axis or spinning counterclockwise about that axis. Okay? This quantum number has the symbol m sub s, or sometimes it's not even given a symbol. And because there are only 2 possible spin states, there are only 2 possible values of m sub s. And so for some reason they chose +0.5 or -0.5. Okay? This is probably because there are lots of other zeros and ones in the table and we don't want more. So for each orbital can hold 2 electrons. One would have the +1/2 spin, and one would have the -1/2 spin. Okay? So those are the 4 quantum numbers. That's how we describe the orbitals that hold electrons, or that give us a probability of finding electrons, and the differentiating between the 2 electrons in an orbital. Okay? So here is the 5 possible orientations of the d subshell, right? So we know that a d subshell has the quantum numbers -2, -1, 0, 1, and 2. And I told you that d's can get a little crazy, right? So it's the sort of 2 lobes that are oriented on different axes, okay? And then there's this one, which is just strange, okay? And so what do these shapes mean? Well, I told you that these are a probability, right? So let's kind of go back. I want to go back a little bit to here. All right, these are usually given as a 90% probability region or an 80% probability region. Okay, that just means that if you have an electron in this orbital, you have a 90% probability of finding it in this area or in this volume in 3D space. Okay, so you generate these shapes on a computer, you plug in these mathematical formulas, and you say, all right, cut it off at 90% probability and give me the volume of that shape. Okay, and so the computer would spit out these shapes. All right, so just to kind of summarize, wrap up, N, L, and M sub L all describe the orbitals an electron is found in. The spin quantum number describes the electrons within an orbital. The number of subshells per shell is N. the number of orbitals per shell is n squared. So since each orbital can hold 2 electrons, the number of electrons per shell would then be 2n squared. So those are all things that you can kind of keep together.